2, 1. We have ignition, and we have liftoff. We have liftoff of the Titan Centaur, carrying the first of 2 Voyager spacecraft to extend man's senses farther into the solar system than ever before.
NASA is on high alert as Voyager 2, drifting at the edge of interstellar space, has begun transmitting unusual signals. The readings defy expectations and leave experts puzzled. No one knows their source or meaning, and every theory raises more questions than answers. Scientists are watching closely, aware that whatever Voyager 2 is encountering could challenge our understanding of the universe and force humanity to rethink its place in the cosmos. Voyager 2's historic launch. On August 20th, 1977, Voyager 2 was launched from Cape Canaveral, Florida, aboard a Titan IIe Centaur rocket. The spacecraft weighed just over 720 kilograms and carried 10 sophisticated scientific instruments designed to reveal the secrets of the outer planets. These included a plasma spectrometer to study charged particles, a magnetometer to measure magnetic fields, a cosmic ray telescope to track high-energy particles, and an imaging system capable of sending the first close-up pictures of worlds never before seen by human eyes. The combination of these tools made Voyager 2 a mobile laboratory capable of exploring both the planets themselves and the space surrounding them. Voyager 2's mission was ambitious from the start. Its primary goal was to perform flybys of the gas and ice giants, Jupiter, Saturn, Uranus, and Neptune, collecting data that would transform our understanding of the solar system. In 1979, the spacecraft arrived at Jupiter, capturing stunning images of its swirling clouds, the Great Red Spot, and the dynamic storms that rage across its atmosphere. Voyager 2 also observed the planet's many moons in remarkable detail, including volcanic activity on Io and the icy surface of Europa, revealing a world more active and complex than scientists had imagined. In 1981, Voyager 2 reached Saturn, providing an unprecedented view of its intricate ring system. The spacecraft discovered small moons embedded within the rings, mapped the planet's magnetic field, and captured detailed photographs of Titan, Saturn's largest moon. Titan's thick, hazy atmosphere intrigued scientists, laying the groundwork for future missions, such as the Cassini-Huygens expedition, which would explore the moon decades later. In 1986, Voyager 2 made its historic flyby of Uranus, remaining the only spacecraft to visit the planet to this day. Its instruments uncovered 10 previously unknown moons and revealed winds moving at extraordinary speeds in the upper atmosphere. The spacecraft also detected that Uranus's magnetic field was unusually tilted relative to its rotational axis, suggesting a complex interior structure. Its faint rings glimmered subtly in sunlight, and the planet appeared as a cold, distant, and enigmatic world, highlighting the diversity of our solar system. 3 years later, Voyager 2 reached Neptune. At its closest approach, approximately 4,800 kilometers above Neptune's cloud tops, it captured images of massive storms, icy rings, and new moons. Winds exceeding 1,100 kilometers per hour battered the planet, and Triton, Neptune's largest moon, showed geyser-like plumes and a surface sculpted by ice and nitrogen frost. The probe's data completely reshaped our understanding of the outer planets, revealing a solar system far more dynamic and varied than ever imagined. After completing these planetary encounters, NASA extended Voyager 2's mission into what became the Voyager Interstellar mission. The probe was sent to explore regions beyond the solar system, to study the heliosphere boundary and the interstellar medium, areas no human-made object had ever reached. Despite traveling billions of miles, Voyager 2's instruments continued to function, sending precious data back to Earth. Over 4 decades later, the spacecraft remains a pioneer at the edge of human knowledge, carrying the story of our solar system and humanity's curiosity into the vast unknown. Surprisingly, the spacecraft launched over 4 decades ago now is sending back signals that challenge everything we expected at the edge of our solar system, crossing the solar threshold. By 2007, Voyager 2 was approaching a boundary no spacecraft had ever crossed before. On approximately August 30, 2007, Voyager 2 passed the termination shock, the region where the Sun's supersonic solar wind begins to slow down dramatically as it encounters the interstellar medium. This area is turbulent, full of charged particles and magnetic activity, and Voyager 2's plasma spectrometer carefully measured the density and speed of plasma, helping scientists understand the behavior of solar wind at the edges of the heliosphere. For years, the probe continued sending back data, gradually moving farther from the Sun's direct influence. Finally, on November 5, 2018, Voyager 2 crossed the heliopause, the ultimate frontier where the Sun's protective bubble ends and interstellar space begins. This was a historic moment in human exploration. The PLS detected a sharp decline in the solar wind's speed, dropping almost to zero, confirming that Voyager 2 had left the heliosphere entirely. The spacecraft had entered a region dominated not by the Sun, but by the galaxy beyond. Simultaneously, the cosmic ray subsystem measured a dramatic increase in high-energy galactic cosmic rays. Particles that had been partially shielded by the Sun's magnetic field now flooded the spacecraft's sensors, while heliospheric particles from within the solar system decreased sharply. Together, these measurements provided the first direct look at the environment of interstellar space, giving scientists unprecedented insight into how the solar system interacts with the galaxy. At the moment of crossing, Voyager 2 was approximately 11 billion miles from Earth. Signals traveling at the speed of light took around 16.5 hours to reach NASA's antennas, making each transmission a long-distance message across the void. Despite the immense distance, Voyager 2 continued to communicate, its instruments functioning decades after their deployment. The spacecraft carried humanity's eyes and ears into a region completely unexplored, offering a glimpse of a universe that had never been measured firsthand. Voyager 2's journey into interstellar space was more than a milestone. It was a testament to human ingenuity, precision engineering, and the unquenchable thirst to explore the unknown. Every reading, every particle detected, brought scientists closer to understanding the boundary of our solar system and the beginning of the interstellar medium. Now, in true interstellar space, Voyager 2 is encountering phenomena beyond our models. And let's now tell you how it still survives to tell the tale. The power struggle. One of the most remarkable aspects of this mission is how the spacecraft continues to operate despite the harsh conditions of interstellar space and the natural decay of its power sources. Voyager 2 is powered by 3 radioisotope thermoelectric generators. These devices convert the heat produced by the radioactive decay of plutonium-238 into electricity. This process is incredibly reliable, allowing the probe to function continuously, but it is not infinite. Plutonium-238 decays slowly over time, and as a result, the RTGs produce about 4 fewer watts of power each year. NASA engineers must carefully manage this dwindling supply. To conserve energy, they periodically shut off non-critical systems, including heaters, redundant instruments, and certain scientific sensors. These decisions are made with precision, balancing the need to protect the spacecraft against the desire to continue gathering valuable data. Over the years, this careful power management has allowed Voyager 2 to maintain operations in its most essential instruments, keeping the plasma spectrometer, cosmic ray telescope, and magnetometer active as it ventures ever deeper into interstellar space. In recent years, a new power management plan has been implemented to extend Voyager 2's mission life. Engineers analyze the energy budget carefully, ensuring that each instrument receives enough power to operate while reducing unnecessary consumption elsewhere. This involves turning off instruments in rotation, monitoring battery performance, and adjusting settings to maximize efficiency. Thanks to these meticulous strategies, Voyager 2 continues to send back data, providing humanity with a glimpse of the interstellar medium, cosmic rays, and magnetic fields far beyond the influence of the Sun. Even as the spacecraft ages, its resilience is extraordinary. Decades after launch, it continues to explore regions of space no human has ever visited. Each system functions not by luck, but through careful planning, engineering, and constant monitoring by NASA teams on Earth. The spacecraft's ability to survive in extreme cold, endure cosmic radiation, and maintain communication across billions of miles is a testament to human ingenuity and foresight. Now the question is, with power dwindling, can NASA preserve Voyager 2 long enough to fully decode the mysterious new signal, or will they be forced to shut down just when the mission is on the verge of its most critical discoveries? Interstellar environment revealed. After Voyager 2 crossed the heliopause in November 2018, it entered a region no human-made object had ever explored. For the first time, it began providing direct measurements of the interstellar medium, a vast space filled with sparse particles, magnetic fields, and cosmic radiation beyond the Sun's protective influence. Its instruments, still functioning decades after launch, allowed scientists to observe a universe completely unknown and to gather data that could redefine our understanding of the galaxy surrounding our solar system. One of the most striking observations came from the plasma spectrometer. Within just a few days around the heliopause crossing, the plasma density jumped dramatically from roughly 0.002 particles per cubic centimeter to 0.0093 particles per cubic centimeter. This sudden change confirmed that Voyager 2 had left the relatively calm bubble of the heliosphere and entered a denser, more turbulent region. The spacecraft also recorded the radial solar wind speed dropping essentially to zero, signaling that the Sun's influence had ended and Voyager 2 was now moving through a completely different plasma environment. Measurements from the heliosheath, the turbulent area just inside the heliopause, revealed pressure variations influenced by energetic particles and magnetic fields, showing that interstellar space was not empty or static, but a dynamic, energetic realm. Scientists could infer additional interstellar parameters using the data, such as neutral hydrogen density around 0.12 particles per cubic centimeter and magnetic field strength approximately 0.5 nanotesla, providing unprecedented insight into the environment beyond our solar system. Energetic neutral atom observations also helped map the complex interactions between the solar wind and the interstellar medium, highlighting turbulent regions that had never been measured before. While these measurements alone were extraordinary, the most shocking development came in the form of a signal. It was unlike anything NASA engineers had expected. Voyager 2, a spacecraft designed to send back scientific readings, began transmitting bursts that did not fit known telemetry patterns. The signal was consistent, structured, and persistent. It was clear that this was not random noise from the probe or space. The discovery sent waves through mission control and the global scientific community. For the first time, the idea that Voyager 2 might be encountering something entirely new beyond the heliopause became impossible to ignore. The strange new signal emerges. Analysts began noticing a series of unexpected bursts coming from the spacecraft. These bursts did not match standard telemetry. They were irregular, yet oddly consistent. At first, the mission team considered technical glitches, instrument errors, or even cosmic interference. But repeated checks showed that the pattern persisted, and the bursts were distinct from normal background noise. As the team studied these signals more closely, a pattern began to emerge. The unusual bursts correlated with changes in plasma density and cosmic ray readings detected by Voyager 2's instruments. During periods when the plasma fluctuated or cosmic ray intensity spiked, the signals seemed to respond. This suggested an interaction between the spacecraft and the local interstellar medium, a dynamic environment that was more complex than models had predicted. The idea that space itself could somehow influence these signals fascinated scientists, but it also raised questions. Could the signals be natural phenomena, amplified or shaped by interstellar turbulence, or was there something more deliberate at work? Engineers carefully reviewed every transmission log. They confirmed that there were no commands sent from Earth at the times these bursts appeared. Voyager 2's systems had not been instructed to generate them. The instruments themselves were not malfunctioning. Each burst had structure and modulation, hinting at organization beyond random interference. The signals exhibited characteristics that challenged conventional understanding of telemetry and deep space communication. It was as if Voyager 2 had become a receiver for something entirely unknown, a probe that had left the familiar and was now reporting signals that defied explanation. The discovery sent ripples through NASA. Scientists began debating all possible explanations, from exotic plasma interactions to unknown cosmic phenomena. Some hypothesized that the probe might be encountering particles or fields that could naturally create complex signal patterns. Others quietly speculated whether Voyager 2 had, for the first time, stumbled upon something entirely new and active in interstellar space, something that might be sending a signal through it. Hypotheses under investigation. As the mysterious bursts from Voyager 2 continued, NASA scientists and engineers faced a puzzle unlike any in the history of space exploration. The spacecraft was millions of miles beyond the heliopause, a region barely understood and entirely unexplored by human instruments. Every team member knew that interpreting these signals would require considering every possibility, from natural cosmic phenomena to highly speculative engineered sources. One avenue of investigation focused on plasma turbulence. Voyager 2 had already measured fluctuations in plasma density, speed, and pressure as it crossed the heliosheath and entered interstellar space. Scientists considered whether shockwaves or sudden pulses in this charged particle soup could interact with the spacecraft's instruments, creating the bursts now observed. These transients had been recorded in other contexts before, but never with the striking pattern and persistence of this signal. Another possibility involved magnetic anomalies. The heliopause is not a smooth boundary. It is a complex region where the Sun's magnetic field collides with interstellar magnetic fields. Subtle fluctuations in these fields could create wave-particle interactions, indirectly influencing Voyager 2's instruments. Such magnetic interactions might produce organized signals, giving the appearance of a deliberate communication where none existed. The cosmic ray hypothesis also drew attention. Beyond the Sun's protective influence, the spacecraft encounters galactic protons, electrons, and heavier particles in high-energy fluxes. Sudden increases or decreases in cosmic ray intensity might couple into Voyager 2's instruments, producing measurable signal artifacts. Previous studies of cosmic ray spectra and secondary isotopes beyond the heliopause have shown that interstellar propagation is more complex than expected, supporting the possibility that these signals are a natural byproduct of extreme cosmic environments. Engineers also explored power system effects. Voyager 2's RTGs are steadily declining in output, and instruments are periodically cycled on and off to conserve energy. It was possible that subtle variations in power delivery or timing could unintentionally produce unusual telemetry patterns, mimicking an organized signal. Careful modeling was required to distinguish real cosmic phenomena from artifacts caused by the spacecraft itself. Finally, some considered a speculative, engineered source. Could there be something artificial in interstellar space, natural or otherwise, reflecting or modulating signals that Voyager 2 could detect? Though highly uncertain, this hypothesis could not be dismissed entirely, as it would account for the structured nature of the bursts. Which of these theories will hold up under scrutiny, and Is NASA on the verge of discovering something truly unprecedented in the depths of interstellar space? The answers remain just out of reach as Voyager 2 continues its silent journey through the void. Risks, stakes, and implications. The unexpected signal from Voyager 2 has transformed what was once a routine interstellar mission into one of the most fascinating mysteries in modern space exploration. For more than 40 years, Voyager 2 has faithfully transmitted scientific data across billions of miles, giving humanity a window into regions of space no human has ever reached. Now, the spacecraft is sending back bursts that do not fit any known pattern, and scientists are both thrilled and cautious. While the potential for groundbreaking discoveries is immense, the signal also introduces serious operational risks. Voyager 2 is powered by aging radioisotope thermoelectric generators, which produce steadily declining electricity from the decay of plutonium-238. Each year, the probe loses about 4 watts of power. If the new signal interacts with critical systems or triggers unforeseen responses, NASA may have to shut down essential instruments or reconfigure power distribution. Doing so could sacrifice decades of carefully gathered data and limit the spacecraft's ability to continue exploring the interstellar medium. Dr. Margaret Guhatha-Kurta, a former NASA astrophysicist, explains, Voyager 2 is operating on the edge of its capabilities. Every instrument we choose to run or power down can have a significant impact on what we learn, and these decisions are more critical than ever given this anomaly. From a scientific standpoint, the implications are profound. If the bursts are linked to plasma turbulence, magnetic anomalies, or cosmic ray interactions, they could challenge long-standing models of the heliosphere boundary and the interstellar medium. We are seeing phenomena at the frontier of physics, notes Dr. John Richardson of the Massachusetts Institute of Technology. Voyager 2 is giving us a real-time laboratory for processes we have only simulated before. This signal may be a key to understanding how high-energy particles behave outside the Sun's influence. The probe's data could provide humanity with the first detailed measurements of regions beyond the solar system, revealing how our Sun interacts with the galaxy and shaping future exploration strategies. The anomaly also raises philosophical and cultural questions. If the signal proves to have an engineered origin, whether natural or artificial, it would force humanity to consider the possibility of non-human intelligence interacting with human technology. Experts such as Dr. Jill Tarter, a pioneer in the search for extraterrestrial intelligence, emphasize that even the suggestion of artificial signals requires careful scientific scrutiny. The discovery would reshape not only astrophysics, but also our understanding of life, intelligence, and our place in the cosmos. NASA engineers and mission managers now face difficult choices. Should they reallocate power to higher-risk observations to capture the full mystery, or scale back operations to preserve the probe's longevity? Each decision carries consequences. Meanwhile, communicating the anomaly to the public adds another layer of complexity. The agency must convey the significance and uncertainty without sensationalizing the discovery or creating unnecessary alarm. As Voyager 2 silently travels through the cold, dark void of interstellar space, its instruments continue to capture data that could redefine our understanding of the universe. Yet the mystery of the signal persists, leaving scientists and the world on the edge of a profound discovery. What is behind this signal? A natural quirk of interstellar space, or something that changes everything we thought we knew? What do you think? Please share your thoughts in the comments.